Okay, welcome to EGR 456. Today's material is super important, and I plan on repeating part of the material when we work out the problems. But this chapter is going to give us some information about filtering, how to smooth the signal, also the important commonly used filter called Kalman filter. Now, in this chapter, we will try to fuse measurements from multiple sensors. So let me set up the stage and give you the background. So in state estimation, we have been looking at how do we get these onboard sensors that are noisy, so and not so reliable. So you have these noisy sensors, and sometimes they give you good measurement, sometimes they do not give you good measurement. So you will never see an accelerometer giving you a straight line, something like this. You will almost always see an accelerometer doing something like this. So you would see the output of an accelerometer is going to vary as the time goes on, even if input is constant. So here is the problem. Output changes even though input is constant. Now that creates a problem, because depending upon how the output varies, it could be a deterministic variation, which means you can program it. For an example, if you have a weighing scale and every time the weighing scale is offsetted by 10 pounds, so you can subtract those 10 pounds and still you can get accurate measurement. But imagine a case where the weighing scale offset changes from 10 pounds to 15 pounds to 20 pounds to 25 pounds to 0 pounds. So in that case, it is very difficult to estimate the true weight. So what we have is we have these noisy sensors. So we have IMU, which has 3-axis accelerometer, 3-axis gyroscope, and 3-axis magnetometer. So we have these 3 sensors and they are noisy. Then we have airspeed or a barometer, that also is noisy. Then we have GPS, and GPS is unreliable. So you may get a good fix, you may not get a good fix. Sometimes you get an accurate reading, sometimes you don't get an accurate reading. So how do we fuse or combine data from these different sensors so that we can estimate the state accurately? And this is an important problem that is studied in a lot of branches of engineering. So why do we need to estimate states? So if you think about it, let's look at the 13 variables that we are dealing with. So if you look at, these are the 13 states, actually 1, 2, 3, yeah, time is not here, so 12 states. Sometimes you have to estimate the time as well. So you have 12 states where you have the position in north direction, position in east direction, position in down direction. You have forward velocities in body coordinate system, UVW. You have roll, pitch, yaw, and then you have PQR. Those are the roll rates. Now, if you look at the GPS can give you some position estimates. Now, UVW can be measured using accelerometers. So you can use an accelerometer. You can use the airspeed sensor. and you can try to get an estimate on forward velocity. Roll pitch yaw you get from gyroscopes and accelerometers. And PQR, these are the rates, angular rates. You get that from gyro. Now, some of these measurements may be directly available. Some of these measurements may not be available directly. So sometimes we have to combine output of one or two sensors to come up with a consistent, good measurement. So estimation is needed because first, our sensors have errors. Second, sensors drift. Third, the measurement is directly not available. So for an example, if you have a measurement, say heading, it may not be directly available. So measurement is derived. And when you are deriving a measurement from two or more sensors, errors in those sensors get added to the output. So all these issues make life complex. So let me give you an example of how bad the situation could be. So let me give you a very simple example. So imagine that you have an accelerometer. So let's assume that you have an accelerometer. So this accelerometer, you mount it on a car. Okay. Right now there is no component of gravity. So this accelerometer is going to measure the acceleration of the vehicle. And this vehicle accelerates in the forward direction. So this is acceleration. The actual acceleration, so A actual, so I'm going to call this A actual, is 10 meters per second square. Actual acceleration is 10 meters per second square. But the measured acceleration is at 10.2 meters per second square. And please understand, it's not going to stay constant at 10.2. It's going to vary. So for an example, if the true acceleration, so let me show you the time here, time, and here is the acceleration. True acceleration is 10 meters per second square. The major acceleration is going to be something like this. It will vary about this. So this is the major. Now what I'm going to do is, from this acceleration, I'm going to find out the velocity. Velocity is acceleration multiplied by time. So if you look at the velocity, the true velocity is, once you look at the acceleration, if you start multiplying that by time, the velocity of the vehicle, say if it is going to start at 0, then its velocity is going to go something like this. This is the velocity. Now, if you look at the actual acceleration, the velocity that is derived from this actual acceleration is going to be, it will have some error. It will be 0.2 times t. This is the error that is going to be in the actual velocity. So if you think about it, your velocity is going to be something like this. So already your velocity is inaccurate. Now let's look at the position. So you have position is acceleration multiplied by time square divided by 2. If you integrate acceleration, this is what you get. Assuming it's starting at 0 position, your velocity, the position is going to be something like this. But now, if you were to use the measured velocity that has some error, the velocity gives rise to this position. This is way off. What it means is, from the accelerometer, you may predict that your vehicle is at location A, but actually the vehicle could be at location B, or it might have not moved. So all this error, because of, please understand, as time goes on, this error accumulates. So here is the problem. So let me start with the problem that we have solved. We are trying to solve. So I have this position, and I'm trying to find out this position from an accelerometer that is noisy. So I notice that, ooh, this is how my position drifts. However, there is an alternative. Here there is a lamppost. So here there is a lamppost. I know exactly where this lamppost is. I know exactly. So this lamppost is at distance, say 10 meters. So as soon as this accelerometer reaches 10 meters, I can, so even though my system is indicating I'm over here, but my lamppost is at 10 meters, I can actually correct it. So I can bring my position back here, and I will treat this as an error. I will treat this as an error, and I will compensate for it. But here is the problem. This error is corrected only at one point. So as Alejandro said, that unless I have reference points that are completely known and do not change during this travel, I am not able to cancel out the error. So what I would do is, imagine there is another lamppost. Then I can actually correct it over here, and I will try to correct it. This is exactly what GPS does. So what GPS signal that you get is, GPS gives you periodically accurate measurement of an absolute location. So what you do is, the error that is generated because of the sensor noise, you sort of eliminate or try to minimize over a period of time. So now here is the issue. I have a sensor and I have another sensor. So this is GPS and this is accelerometer. So GPS can give me solutions, but it cannot give me solution at 100 hertz. But acceleration, I can integrate at 100 hertz. So what I want to do is, I want to smartly combine this measurement, and come up with the best possible estimate. Best possible estimate. And this is a very important problem. And you will see, sometimes instead of a GPS, you can have cameras. And those cameras are used for landmark matching. So you see a certain landmark, and then inside the map information, you have the absolute coordinates of that landmark. Landmark is matched, so you know your vehicle is at that location, and then you actually something called as you dead reckon. So you dead reckon. So you cancel out the error at that instant. But in the case of that aircraft, the problem is in multi dimensions. So for an example, you have the position in north direction, position in east direction, and position in down direction. and you also need to estimate the velocities. So somehow we have to come up with some sort of smart mathematical algorithm. So the objective here is come up with some sort of algorithm that gives us best possible outcome, something like a least square result. So that is the fundamental purpose of state estimation. So now what we are going to do is we are going to see how can we find out uh, these states, how can we get best estimate on the states. There is something called as a benchmark maneuver, and this benchmark maneuver is a sort of a step input. Yeah, so what I meant by that here, this is error plus 10 times t. So if you look at, there is something called as the benchmark maneuver, which means what happens if you suddenly change the altitude from say 100 to 105, go down to 95 and go back to 100. Ideally, what you would anticipate that at the end, your measured altitude should be 100, but you will notice it will never be 100. Same thing happens with chi, which is the course angle or the commanded course. So you apply certain course variation and then see if you go back, can you go back to the original course. So you started with 0 degrees, you gave it an input, maybe 30, minus 30, and then you went back to 0, and you want to see if your measurement system that takes the data from IMUs, gyroscopes, compass, GPS gives you the same output or not. So there are multiple ways this can be done. First and foremost, I'm gonna give you a very simple approach. And this approach works when the vehicle is moving very slowly. So, and in the book, it is called as inverting. It's a simple inversion. So what I'm gonna show you here is a very simple approach. So think about what I have here is I have an accelerometer. So I'm going to show you an accelerometer, and I have a gyroscope. So I'm going to show you the chip. And this hypothetical chip, just bear with me for a second when I discuss the concept. So this is a hypothetical IMU unit. So this is an inertial measurement unit, IMU. And in this hypothetical measurement IMU unit, I have two accelerometers. So I have one accelerometer in this direction. I have one accelerometer in this direction. So I'm going to call this AX, and I'm going to call this AY. So I have two accelerometers, AX and AY. So for an example, if you move this accelerometer in this direction or in this direction, you will see some output along AX. If you move this accelerometer in Y direction here or minus Y direction, then you will see some reading. And in addition to this accelerometer, there is a gyroscope around this axis. So you have a gyroscope. I'm going to call this GY. So this inertial measurement unit has an interesting property. It has an accelerometer in X direction. Sensitive direction is X. So let me show this is X. Sensitive direction is Y. So it has AY, and it has GY. So this accelerometer, this gyroscope can measure the rotational rate in this direction. So if you rotate this chip around Y direction, you will get some sort of rate output. So this is a very hypothetical accelerometer. Everybody understood? This is the accelerometer that I want to discuss, sensor fusion. And here is the, the problem that I want to solve. I'm going to mount this accelerometer. I'm going to mount this accelerometer on a platform that is hinged at one end. So this is a platform, this is the hinge, and this is the hinge. So this is hinge, and this is the platform. And this accelerometer is mounted over here. So if I were to say this is AB, this is how the accelerometer is aligned. So what it means is this is its X direction, Y direction is coming towards us, and the accelerometer, the gyroscope is going to measure the orientation about O. Yes, Borna, hold on, just a second. Let me answer that question. Now, what I'm going to do is I'm going to move or rotate this platform about O. So what I'm going to do is I'm going to elevate this platform a little bit. So obviously this accelerometer, the IMU will get elevated. I'm going to do it something like this. It will get elevated. And what I'm going to do is, here is what I want to find out. I want to find out instantaneous angle. So I want to find out what is this theta. I want to find out after some time, what is this theta. Now, there are two ways this is done. So think about it. This is, I'm going to call that the original position. Then I'm going to call this the middle position. And I'm going to call this the end position. Now, what I want to do is I want to find out the angles theta M and theta E. Now, let's look at two cases. Case one. In case one, it's static. What it means is initially it will be at the origin. So if you look at, if it is at origin, you agree with me, the component of gravity is going to act in the vertical direction, and component of gravity will always be acting in this direction. So first, the accelerometer in X direction, at origin, here AX is going to measure 0. What happens here? Here, this is the direction of AX. And again, I'll just show you, this is the direction in which gravity is acting, and accelerometer is going to measure G. So if this is my G, this is going to be G cosine theta, and this is going to be G sine of theta. So AX would measure G sine of theta M. Then here at this location, AX would measure G sine of theta E. Any questions here? And clearly at origin, theta is 0. So sine theta is 0. So everything is fixed. So this accelerometer is not moving. This accelerometer, think about it, is it glued? This accelerometer is glued to the platform, and the platform is gradually rotated. So what it means is, in other words, as I rotate the platform, and this is an important exercise, as I rotate the platform, my measurement AX is equal to G sine of theta. So if I want to find out the value of theta, if I want to find out the inclination of the platform, I actually find out the measurement of AX, divide that by G, and find out its sine inverse. Everyone understood this? So for the sake of discussion, let's say a accelerometer output AX is maybe in terms of it gives you say meters per second square. So it gives you 8 meters per second square or 6 meters per second square, or when it is vertical it gives you 9.8 meters per second square. So what you will do is you will substitute the value of AX. So if it is A as 8, so you will 9.8 and do sine inverse, and then you can find out the value of theta. So Borna, bear with me. I will answer all your questions. But so everyone understood? Now my question to you is this. This approach is valid as long as I start at origin, go to the middle position, stay there for some time till the output of the accelerometer stabilizes. This is extremely important. So what I do is I rotate, I go to middle position, I stay there for few minutes till the accelerometer output stabilizes, get that value, find the value of theta, then move again to the end position, stay there, and get the value of theta again. Everybody understood this? So what I'm trying to do here is this approach will give me good results as long as I stay at the origin for a finite time, stay at the middle position for the finite time, and stay at the end position at finite time. And assuming I have super fast accelerometer, it may be possible to come up with some sort of quasi-static case. So for an example, case 1 is static. I can find out value of theta at origin. I can find out theta at middle. I can find out theta at end. Case 2 is very slow motion, very slow motion. In that case, I can find out the value of theta 0 is 0. I can find out theta m, but here, and this is going to be some non-zero. So just to give you an idea, I will say 45 degrees. And if I have the time values, say t0 is equal to 0 seconds, tm is equal to 10 seconds, I can approximately find out theta dot at 45 divided by 10 degrees per second. This is approximate. I can repeat the same procedure. I can go to theta end, and if theta end is say 70 degrees and TE is equal to 20, I can find out theta dot as 70 minus 45 divided by 20 minus 10, and that gives me degrees per second. Do you agree with me? Any questions here? Now what I want to do is I want to increase the graduation. So instead of measuring at only at 3 locations, so 0, the middle location and the end location, I will try to repeat this exercise at intermediate points. And why am I going to do this at intermediate point? With a hope that I would be able to get better estimates on angular rate. So better estimate on angular rate. So multiple measurements of theta and time. Now here is, yeah, this is all happening in the code. But now let me ask you this question. This may work very well for a very slow motion, but as soon as you increase the speed beyond certain threshold, you can visualize that these measurements are going to be off. So let me do this case. So now, same example. You have IMU, and now this is going at a slightly higher speed. So as soon as we start doing this, our logic theta is equal to sine inverse of AX divided by G. This will not give good results if theta dot is large. However, at that point, I see that I have a gyroscope, and this gyroscope is able to give me rotation rate around this axis. So this is the theta measured from accelerometer. This is the theta that is measured from accelerometer. Now what I can do is I can measure the theta from gyro, the gyroscope. So gyroscope is going to give me angular velocity. So I can find out the angular velocity and multiply that by the time. And I can find out the instantaneous angle. So imagine this gyroscope can give me angular rate or angular velocity, which will be degrees per second multiplied by second. That should give me the in degrees. So this will be the gyro is gonna give me rate. So I'm gonna just say it's omega multiplied by t. Omega is the angular velocity by gyro, and t is the time. So this has to be delta t, difference between the previous time and the next time. Now here is the issue. If this motion is continuously changing, if this motion is quite fast, then the gyro should be able to give me good measurement. The gyro will act just like a tachometer. So basically you mount the gyroscope and continuously get the output. As long as this angular velocity, this omega bar, is constant and continuous, you would get a good output from gyro. Now here is the problem. What I want to do is I want to start at the origin. I want to slowly take it to an intermediate position. I want to slowly take it to other position, but I may stop or I may continuously go. So the angular velocity omega bar is not constant. So what I have is I have some sort of start stop type of motion. So what I need to do is, so I have two values of angle. So I have angle that is predicted by an accelerometer and angle predicted by gyroscope. So here is what is happening. Accelerometer gives me good output. So good or accurate when it is moving slowly, when it is moving slow. And gyroscope gives me good output when it is moving fast. So somehow what I need to do is I need to combine these two values. So here is how I would formulate this. Now, before I go further, I just want to show you here. I'm going to introduce an important filter, which is called as complementary filter, which is sort of a precursor to the Kalman filter. We'll work out the same problem later using the Kalman filter. But now everyone understood the issue that we have is if my measurement is changing slowly, I can rely on accelerometer. If my measurement is going fast, I can rely on gyroscope. So how do I combine these two together? So here is the question. How do I combine? How do I combine theta A and theta G so to get theta hat? And I'm calling this theta hat because this is estimated angle. Okay, I'm gonna give you a minute to think about this problem because this is the fundamental problem in estimation. I have a measurement that is accurate and inaccurate based on certain characteristics. So how do I take best of the both worlds? Any suggestions? Yeah, there is no observer here yet. Subir, no observer yet. That we'll go with the observer when we talk about Kalman filtering and all. But there is no observer. And as a matter of fact, I would like to question the very basic notion of observer. So hold on for a second. So how would you do this? How would you combine? So here is, can I write this equation and then tell me if it makes sense? Theta hat is equal to theta A plus theta G divided by 2. Now, what that means is when it's moving very, so their average. Yeah, of course, there is an error. I completely agree. There is an error. But what I want to do now is I want to minimize. So here is how it's going to happen. So what I'm going to say is, I would say 0.5 theta A plus 0.5 theta G. In other words, and this is an important expression that I want to write here. I want to say 1 minus 0.5 plus 0.5 times theta G. Theta A plus theta G. So what this tells me is if somehow, if I can get this mixing coefficient right. So here is what I'm going to call this. And I will rewrite this expression something like this. Theta estimated is equal to 1 minus alpha theta A plus alpha theta G. And in this particular case, alpha, let's assume it to be 0.5. Now, what I'm going to say is, when I'm moving very slowly, when slow, I would say alpha is equal to 0. When fast, alpha is equal to 1. Do you agree with my argument? So I'm going to call this alpha for the lack of, just loosely speaking, I'm going to call this a mixing coefficient. I'm going to call this a mixing coefficient. Yeah, Borna will get there. We will get there. Just hold your horses. We'll get there. So now alpha is my mixing coefficient. So somehow what I'm going to do is, I have this knob which I'm going to tune based on whether it's moving slowly or it's moving fast. So when it's moving slow, I would use alpha is equal to 0, which means my estimated state will be equal to the measurement of the accelerometer. And when I'm moving fast, I would change my alpha to 1, and alpha would vary between 0 and 1. Now, I want to pause here for a minute and make sure that we understand this concept. Everyone understood that this mixing coefficient is changing. And this mixing coefficient is dependent on how fast or how slow this platform is moving. Any questions here? Does this argument make sense? So now our problem is that how do we decide this value of alpha? Alpha, how to decide? Now, one thing that I can do is, I would just say my alpha, so let me write this expression down. Theta is equal to 1 minus alpha theta A plus alpha theta G. So this is the angle from accelerometer, and this is gyro angle. So what I'm going to do is, at the first cut, I'm going to say, what happens if I choose my alpha? What happens if I choose my alpha close to 1? If I choose my alpha close to 1. So what I'm going to do is, I'm going to choose my alpha, say 0.95. I'm going to choose my alpha 0.95, and I'm going to say it's a constant value. So which means my filter equation is going to look like 0.05 theta A plus 0.95 theta G. So at the first cut, I'm going to assume this. Now I want you for a second to visualize what happens to this measurement. I want you for a second to visualize what happens to this measurement. This measurement comes from accelerometer. This measurement comes from gyroscope. So to get that, you should have a high value of omega. In other words, you should have theta dot g. So what would happen if theta dot g, so this is what will happen. If theta dot g is a very high value, if theta dot g is very high value, estimate will be about 0.95 times theta g. And I want you to be absolutely clear about this. Imagine that you have this platform, and you are moving this platform very fast. If you are moving this platform very fast, you are going to get a high value of theta dot g. And to get theta g, you need to have theta dot g. If there is no theta dot g, there is no theta g. Because theta g is theta dot g, which is the angular rate multiplied by the time. So which means my estimate is going to bias towards the gyro output. So when my theta dot g is very high, my angle is going to bias towards theta g. Now let's understand. Yeah, Borna, hold on. Now let's assume if my theta dot g, is small, if my theta dot g is small, then you agree with me, my theta will be biased towards theta A. You agree with me? But here is what's going to happen with theta A. This is actually a function of time. This theta is computed as a function of time, which means initially you would have an error. So initially you would have an error, but as time goes on, this error would minimize and your measurement would converge to the acceleration value. So what would happen? Because at that time, your theta g is going to be 0. So even though you have 0.95, it's multiplied by 0, but you have theta a, that accelerometer, it will continuously get accumulated. And because of this accumulation action, your theta will gradually go towards the angle that is measured by accelerometer. Now this all is happening when alpha is constant. So what I could do is I can try to be smart and I can change my alpha value to as 0.9 or 0.85, so that to make sure that my output is reaching the actual value. So if you think about the values that you are getting, your estimated value is continuously getting added. So what it means is slowly your measurement will bias, or slowly it would go towards the value indicated by the accelerometer. But here we can do something smart. And something smart is, once again, let's go back to the same equation. My equation is this: estimated theta is equal to 1 minus alpha, theta measured by accelerometer, plus the mixing coefficient, theta measured by gyro. And I know how fast or how slow this platform is moving. How fast or how slow this platform is moving is an indication. It can be measured using the output of the gyroscope. So, and this is important. So if this is the value of omega, I can measure how fast or slow platform is changing orientation by gyro output, which is, I'm going to call this theta dot g. So why not to come up with some sort of relationship? Why not to come up with some sort of relationship wherein you have alpha on y-axis and your gyroscopic rate is on x-axis, and the value of alpha varies between 0 and 1. So what it means is when the gyroscope is very fast, which means this is high value, this is 0 value. So maybe you have some sort of a straight line wherein alpha is dependent on theta g. So let's look at the case. When theta g is 0, my value of alpha is 0. When theta g dot is 0, value of alpha is equal to 0. When my theta g dot is equal to max, my value of alpha is equal to 1. And boom, I got a variable mixing filter wherein I am changing, this is important, changing alpha, which is also called as the gain, depending upon how fast or how slow the platform is moving. And this technique may work for this simple application. Now, before I proceed further, so this is the expression for a complementary filter. Why it is called as complementary? Because the angle measured by accelerometer and angle measured by gyro, they have different accuracy in different operating ranges or different operating conditions, but they are complementary. Accelerometer angle is accurate when it is moving slowly. Gyroscopic angle is accurate when it's moving fast. So if you combine these using some sort of uh, mixing coefficient, then this is called as a complementary filter. Now, the key idea here is we looked at the complementary filter when mixing coefficient alpha is constant. We also came up with some algorithm, intuitive algorithm, wherein we are saying that our mixing coefficient changes from 0 to 1. Our mixing coefficient changes from 0 to 1, and that is dependent on how fast or how slow the orientation is changing. And this perhaps would be good for simple application. But for complex application, you may have to change this algorithm again with some sort of model-based algorithm. And that is where the Kalman filter comes in the picture, and observer, dynamic observer. So if we base all speed related measurement off our gyro output, yes, but there is a problem, because your gyro is not never gonna give you 0. If you look at the gyro output, it's always going to be varying about 0. And on top of it, gyros have something called as startup bias, which means the gyros, when you power them on, sometimes they will start at 10-degree bias, sometimes they will start at 0-degree bias, sometimes they will start at 120-degree bias. So you have something called as startup bias. Then you have something called as noise. And sometimes you have something called as thermal drift. So which means as the temperature increases, the output of the gyroscope changes. So again, you have to calibrate it, but calibration would minimize, but will never eliminate these errors in typical sensors. For an example, if you have a random error, stochastic error, by calibration, you can minimize, but you cannot get rid of it completely. So we'll talk about using some interesting mathematical algorithms. So a fair warning, and I want to give you this warning here. So you will see complex mathematics ahead. So you are going to see complex mathematics ahead. And it may so happen that we may not fully understand the equations, but it's like driving the car. You don't really have to know how the engine works to drive the car. So what we are going to do is we will talk about the equations, but I will try to give you physical interpretation. So most likely how they can be used, what are the applications, and at the end, we will use our software of choice, MATLAB and Simulink, to implement either Kalman filter or extended Kalman filter or some sort of sophisticated filtering algorithms. So we don't plan on reinventing the wheel. So you will see the math. And again, the math, what we are going to see is, again, very superficial. So people have spent their lifetimes studying Kalman filter, extended Kalman filter, particle filter, so on. So I will give you physical understanding. So how it works, what is the application of it, and then we will refer to the MATLAB Simulink toolbox on Kalman filter, and we will use that toolbox to actually perform the filtering and estimation. So warning again, you are going to see complex math ahead, but don't get scared. We are interested in how to use it than completely understand nuts and bolts of the mathematics. Okay, any questions before we dive deep into the system? Okay, so let's see. The first and foremost, which is the easiest way, the system, you can find out the orientations, is called inverting sensor measurement model. And wait a second, can you see that I actually discussed inverting the sensor measurement model over here? Can you see in here, we actually inverted sensor measurement. So we inverted this sine function, that is nothing but inverting sensor model. So how it is done? So there is something called as low pass filtering. So just to give you an idea, what is this low pass filtering? Imagine that you have a signal. You have a signal and that is noisy. And there is a high frequency component and a low frequency component. You pass this through a mathematical algorithm, sort of a filter. Think about it as like a strainer. And what happens is this removes all high frequency component. So here is this high frequency component, high frequency component, high frequency component, and then it gives you a very smooth signal. This is called as low pass filtering, LPF. And low pass filtering has something called as cutoff frequency. So what this low pass filter will do, so this is like a gatekeeper. So if the frequency is below this uh, threshold, say 10 hertz, this frequencies will not, I mean, if the frequencies are below 10 hertz, those frequencies will get passed, low pass. All other high frequency signals will be blocked. So low pass filter will eliminate or minimize the noisy high frequency signal, because typically noise is always high frequency. So what you do is you have an output from the gyroscope. You can make it low pass either in software, or you can make low pass in hardware, or you can have sensors with different bandwidths combined together, and you can construct a low pass filter. There are various ways you can construct the low pass filter. You can construct a low pass filter using resistor capacitor network, or you can construct a low pass filter using a software algorithm. And we will talk about it in just a second. So here is the basic idea. So you have gyro. This gyro is going to give you, this gyro is measuring about x axis. This is the rate about x axis. This also has some non-zero offset or bias. So it has a bias or offset. And it has some random noise. So whatever you measure with that gyroscope has the actual true value. So I'm gonna call this true value. This is true. But it is corrupted by a bias and a random noise. Same thing happens with the gyro, which is measuring along y direction. Same thing happens with the gyro that is measuring along z direction. So when you have this uh, input, you filter it through a low pass filter. If you have low pass filter, LPF, the random noise, which is usually a high frequency component, gets filtered out. If you have a random noise, it gives you a high frequency random noise. And that when you do a low pass filter, you somehow cancel out majority of the random noise. You cancel out majority of the random noise. So you get an estimate, and it is very important. This is not the actual value of P. This is P hat. Hat stands for estimate. You get an estimate of the angular rate about X. You get an estimate of angular rate about Y. You get an estimate about angular rate about Z. And since bias is usually constant, you can cancel it out. Same thing happens with the pressure. You have the true value. This is the true value. This is the true value that is corrupted by bias and noise. So this is bias and when you do low pass filtering, you minimize the noise and bias. It's a constant value, so you can actually take it out. Now, what is this inversion? So in inversion, what we do is we exactly find out the values of the roll rate. We find out the values of roll rate and pitch rate. Just a minute here. Let me go back to the platform example. And now, just a second, I want you to visualize this is an aircraft. Now, can you see that I am able to estimate the pitch angle, which is theta, with all this mathematical jugglery that we did. So imagine instead of this platform, it's an aircraft, and this IMU is attached at the center of the aircraft. So now when I invert this, when I invert here, I got the pitch angle. So I can do the same thing here by doing the complementary filter. Only thing here is what I need to do is this roll rate estimation, pitch rate estimation, and yaw rate estimation can be obtained using the low pass filtering of the gyro input. And then maybe you can add a complementary filter along with accelerometer to make the estimate of the roll angle, pitch angle good. You cannot estimate yaw because, okay, let me ask you this question. So this argument, what I'm saying here is, if you have an aircraft, say if you have an aircraft, this complementary filter argument that we talked about may work to find out the pitch and the roll, but not yaw, because there is no component of gravity in the yaw direction. So you can estimate pitch and roll using complementary filter or model inversion. You cannot do that with yaw. So you can do the exact same thing for the altitude and the airspeed, and you may be able to get good estimates when your aircraft is very slowly moving. But this algorithm or this approach is not expected to work when the system is moving fast or when the dynamics is large. So let's go back and see what are we talking about. So if you look at the output of the accelerometer in x direction, when you look at the output of the accelerometer in x direction, this is what you are going to get. This is the output of the accelerometer in x direction. This is the output of accelerometer in y direction. And this is the output of accelerometer and in z direction. These are nothing but your equations on the Genesis block. So these are the 12. Out of 12, I'm just stating here 3 state equation out of 12 state equations that we studied so far. So that is exactly what is happening. And for a minute, assume the aircraft is not accelerating. If the aircraft is not accelerating, all these values, u, v, u dot, v dot, w dot, omega, v, all these values, they cancel out. And what do you get? Remember this expression? This is the exact same expression that we used to find out value of theta. Sine inverse of ax divided by g. Same thing you can do with y, but in y, what you can do is you can find out to find out roll, you divide these two, and this gives you the pitch angle, and this gives you roll angle. Yaw not possible. Because you do not have a component of gravity. If you want to do x, yes, you can. Actually, there is different way of doing this. You can find out the theta from x, and then you can find out its cosine value, and then there are multiple ways it can be done. X acceleration is going to give you the value of theta. So x acceleration, this is x, is going to give you value of theta. You can use this value of theta to find out value of phi. So there are multiple ways it can be done. So this is output in acceleration output in X direction, in Y direction, and Z direction. So these three are different accelerometers. So Y acceleration X is the accelerometer in the X direction. Y acceleration Y is the accelerometer in Y direction. And then you have Y accelerometer Z is the accelerometer in Z direction. But you can use X, find out the value of theta, and then use this theta in this equation, use this theta in this equation, and then find out the value of phi. Oh, IMUs will have AZ component. So, okay. So basically, okay, this needs an explanation. So yaw means psi, okay, yaw angle. But imagine you have aircraft, and for a second, I want you to visualize the aircraft has rolled. Now, as soon as you roll the aircraft, the initial y gets rotated. This means initial z gets rotated. So let me try to show you. So this is the initial, this is the aircraft. And right now, this is your AZ. Now, if your aircraft rolls, what will it measure in Z direction? It will measure the component of gravity. Now imagine a case when your aircraft is pitching and rolling. So when your aircraft, so for that, I need to show you a three-dimensional figure. Consider that your aircraft is pitching and rolling. So it pitches and it rolls. So you will have all three accelerations. But so please note, psi not present. So yaw. So you can find out roll, you can find out pitch, but in any of these equations, psi or the heading does not come in the picture. And this will need a little bit more discussion, and I plan on doing this again little bit in next class. But what I want you to understand is, if you have accelerometers, if you have a three-dimensional accelerometer, to be honest with you, to find roll and pitch, you just need two accelerometers. So if you look at the system that we started with, if you look at the system that we have with two accelerometers, we can find out roll and pitch, no problem. But here, you can actually use, it's assuming that you have a triaxial accelerometer, which means you are getting the accelerometer component in X direction, you are getting the gravity component in Y direction, and you are getting the gravity component in Z direction. And then this is how you will be able to find out the roll and pitch. But one thing I want you to understand, nowhere in this equation is psi or heading. So you cannot find out the value of yaw, or you cannot find out the value of psi from just accelerometers. You need compass. Okay, I'm gonna just discuss one more thing here. So again, using the complementary filter or just using the pure accelerometers, you are able to estimate the values of roll and pitch. You cannot find yaw. You can estimate the values of roll and pitch, and this is how it would typically look like. All right, I'm going to stop here today. but I will pick up again from here, and I will discuss uh, these equations a little bit in more detail, and then we will go to the advanced concept. So I'm going to stop recording.